Hi everybody, welcome to another video in Math 1332, section 1.3, problem solving. So this is very broad topic. We just go over a few examples in this section, but most of the problems can be done using these four very general steps. Of course, we have to know what is the problem. So we have to understand the problem. By just reading the problem, highlight the important things. And next, we devise a plan to solve the problem. And then we execute that plan and check the answer so that the answer makes sense. Right. Actually, it sounds easier than it actually is. We'll try to follow that. Right, just go to the first example here. A gardener is asked to plant 8 tomatoes plants that are 18 inches tall in a straight line with 2 feet between each plant. So always underline important things. So there are 8 tomato plants, 18 inches tall in a straight line, 2 feet apart. Right. So that's important information. Now we'll draw a line because that's where we plant the tomato. Right. So and the 2 feet between them. So this is the first one, the first plant, and there are 8 of them. We'll just keep doing that. One, two, three, four, 5, 6, 7, 8. Right, and according to the problem, it is 2 feet apart. And then so on. So how much space is needed between the first plant and the last plant? And so we just count 2, and the space in between them, there will be 1, 2, 3, 4, 5, 6, 7. 7 space times 2 feet, 8. So 2 times 7, 14 feet. So right, so 7 times 2 feet is 14 feet. Right. Next, can you devise a formula to find the length of any plants, any number of plants? So first, if we talk about any number of plants, so let that number be n. Right? And then we take a look at this. If there are only 2 plants, there are 1 space. 3 plants, there are 2 space. 8 plants, there are 7. So there's always 1 less than the number of plants. So if n is the number of plants, we can say that there will be n minus 1 spaces between the first and the last plant, the first and the nth plants. Right? 8 of them, 8 plants, there's 7 space, and so on. So each space is 2 feet. So space between first and last, and each space is take 2 feet. So the total is n minus 1 times 2 feet. So that is the general formula for it. Of course, we should check and make sure it makes sense. If there's 8, there's 7 times 2, so that's good. Right, so pretty much just that. One thing I wanted to note here in this problem is, even though we are given this information, we're not using that at all. So sometimes we have more information than we need, and we just use what information that we need for the problem. Right. Next, a campus group is setting up a rectangular area for tailgate bash, and they have 100 feet between two roads to use as width and 440 feet of fence to use. What length we use up the total amount of fence and enclose the biggest area. So once again, highlight important things. We're going to have the rectangular area, right? And they have 100 feet between the two roads and 440 feet of fence to use. What length we use the total amount of fence and enclose the biggest space, right? So just going to draw it. So there's a road, a street, and there's 100 feet apart. And then we'll try to fit a rectangular here. So we can make a rectangular around that, or we can make it use the total width of 100 feet and that. Right. Of course, if we want the maximum area, the one with the biggest area, we want to use the whole 440 feet, right? So we're going to construct a rectangular, just use the whole width. Like that, right? So in that case, this will be 100 feet and 100 feet. And we have 40 total. Subtract those 200. That leaves us 240 feet for the size. And cut that in half, we have 100 by 120. Right, so it's 440 feet. Subtract 200 feet for the size here. You have 240 feet for the length. And we divide that by 2. That gives us 120 feet. So the size of the rectangular area is 100 by 120 feet. Right. Next. Of course, when we have the number, we should check to make sure that the number is reasonable. Of course, they all add up to 440, and the area will be biggest. Right. By paying 100 cash upfront and a balance of $20 a week, how long will it take to pay off a bicycle costing $680? So once again, highlight the important things. $100 cash upfront, $20 a week, and the payoff a total of $680. So we working backward. We start with $680. Subtract $100. That kind of a down payment or cash upfront. That gives us $580. And then we divide by $20 a week. So $580. So this is for the weekly payment. And if we divide that by 20, that's 29, and so we tax 29 weeks. Right, just like that. And that makes sense if we check the math. 29 weeks times 20 plus Let's just check here. We start with 100 and we have 29 weeks, $20 each. And if we check the math, that will be 680. So that check out. Alright, our next problem is a little more interesting and the solution a little bit indirect. So it's a new high in chart buying $12 prices. So we need 12. I said it's math problem. Usually we focus on the numbers and $110 to spend. The boss is thinking insulated cups and smartphone stand. Mugs cost $11 and the cell phone stand $8 each. How many should you buy? Now, of course, this is the idea here. The corporate world is kind of funny that about budgeting. It's considered a good thing to spend as much as the budget amount as you can. So we try to get as close to $110 as possible, and we have $12 price. So that's why we sum up the problem. Right now, so we're going to need $12 prices, $110 each, $110 total. And but the price is $11 and $8 for each item. So in that case, just draw a table, just list out most of the scenarios and just try and error pretty much. Right, so we do as follows. Right, so we start with mugs or insulated cups, and then we do the cell phone stand, and here is the total money. Total amount of money. Right, so we just try and error pretty much. Right, now let's say we need 12 items, right? What if all 12 number mugs? What will be the cost then? Alright, $11 each, right? So that's $132. Certainly way more than 110. So that's why that's not what we want. Now, by the way, if we want 12 mugs, that means there's no cell phone stand because we need the total of 12 items, right? 12 mugs, no stand, the total 12 items. That makes sense. Right, and on the other side of things, if we choose all 12 cell phone stand and no mugs, that will be 12 times 8, $8 each. Cell phone stand, that's $96. So this is way less than 110. So somewhere in the middle here will be good. Well, so what exactly it is? Well, if it is exact number, that would be great. But the idea is it just need to be less than 110. So we just need to list a bunch of different scenarios. So either we can state, how about if we have just 11 mugs? In that case, there's one room, one space for the cell phone stand. So what is the cost then? Well, $11 each mugs and 11 mugs plus one cell phone stand at $8. That gives us 121 plus 8, 129. Right. Either we do that or we increase the number of mugs and so we have 1 mugs and 11 stand and so on. Right, again we just keep going with this, just going down until we have a number that is below 110. Then we stop. That is the good solution. Right, now just keep going here. What if we just have 10 mugs and then will be 2 stand? Just trial and error, right? 10 times 11 plus 2 times 8. That's 110, 16, 126. Of course, we can just keep doing this, but notice the pattern here. So what is the pattern? The mux is $11. Cell phone stand is 8. If you replace one mug by one stand, the cost will go from $11 to $8, right? So if we decrease the number of mugs and increase the power, the number of stand, the cost will reduce by $3 each time we do that. As you see, minus $3, and then minus $3. Deductive reasoning gives us that if this pattern will continue, so we don't have to do all the math, the exact math like this every time. If this is 9 mugs and 3 stand, the total will be subtract $3 from here. So that will be 123. Don't have to do any math for that. Just subtract 3. Don't have to actually calculate it. Right, so there's a long way to go there. Now if we have 8 mugs and 4 stand, that will be 120. Right, just keep subtracting 3. And 7 and 5, that's 117. 6 and 6, that's 100, and subtract 3, 14. And if we have 5 mugs and 7 stand, that's 111. We need one more. If we have 4 mugs and 8 stand, that will be 108. Now that is below 110, so this is a good solution. Of course, anything below this would be good, but this will be best because that is the closest to 110 as possible. So the solution here we have is 4 mugs and 8 smartphone stands, and the total is 108. Right, so that is our solution. If we want to check, it's very easy. 4 mugs of $11 each, so that is $44. And 8 stand at $8 each, so that is $64. And add up that 108. So that check. So it's good. So this case we just do trial and error, pretty much. List all the possible scenarios and then pick out what will be the best. The next problem, kind of similar way, just list all the possible scenarios. But whenever we list out the scenarios, we need to list all of the possible scenarios. And if we are a little more systematic, it will be easier to do, and we will not lose any scenarios. Right. You are an engineering and you have tried to program an automatic gate that will take 50 cents toll, and you have to take only exact change and no pennies or $50 or 50 cents toll. How many combination must you program the gate to accept it? Right. So if we're not using the pennies and $50, we have the nickels 5 cents, the dimes 10 cents, and the quarters 25 cents. So we use the combination of those coins. Right, so here are the coins. The 5 cents, 10 cents and 25 cents quarters. The total is 50 cents. Right. Now, usually, let's say if you have the whole bag of coins, infinite amount of coin, and you actually get 50 cents from it, the easiest way is just go and grab 2 quarters, right? So if you have a choice of any coin, the easiest way to is just pick out 2 quarters for 50 cents. So that makes, so that's where we start with, is we have 2 quarters and no dimes needed, no nickel needed. So that, of course, that $50, 50 cents. So that check. So that's good. I just put a check mark there. The total 50 cents. Right. Now, of course, that's the easiest case. Next is, what if we only have 1 quarter, right? Of course, we don't want to use all dimes or all nickels. First, we want to have a lot more systematic way to do that. So let's say, if we don't have 2 anymore, there's only one scenario. Say, what if we just have 1 quarters, and we still need 50 cents? So, how would we do this? Now, if we have 1 quarters, that means we have 25 cents. We need 25 cents more. All right. For 25 cents, if we use the least amount of coin, we can use 2 dimes and then 1 nickel. So that's 50 cents, right? Now, what if we don't have 2 dimes, we only have 1? So that is 25 cents, 35 cents, and there will be 15 cents left. That requires 3 of them. That also 50 cents. Now, if we also have 1 quarters, but we do not have any dimes, so that means we need 25 cents, and all of them in nickels. Have to be 5. So the idea here is we start with the biggest coin, biggest amount, or the biggest value coin. We can have maximum of 2, right? Now, what if we don't have 2? We only have 1. What other scenarios do we have? And those scenarios are those. Now, those will be all the scenarios where we have exactly 1 quarters. But if we have 0 quarters, well, that means we can have the next highest value coin will be the dimes. We can have all 5 of them. And that also check. Now, if we still have 0 here, but now we'll reduce the number of dimes to 4. That means there's 40 cents here. We need 2 nickel to make it 50 cents. And then if you have 3 0 quarters, but only 3 dimes, that means there have to be 4 nickels. And then the 2, that have to be 6 here. And if we have 1, that would be 8. And if there's 0 and 0 dimes, we need 10. So let's check. Right. So that is all of the scenarios possible that we need to program for this automatic gate. Have to take all different combination here. Right. So a little more systematic here. If we base on the highest value coin, we start with 2, and then we go to 1, and then we go to zeros. Right. Yeah. So that's that. Next, nutritionists often say that you need to burn 3,500 calories while exercising to set 1 pound of excess body fat. In general, that an average person will burn 100 calories walking 1 mile. So, how many miles per day would an average person have to walk in order to set 1 pound of body fat in 1 week? So, 3,500 calories to set 1 pound of fat. Exercise that are 100 calories is like walking a mile. And how many miles per day? And you want in a week. Assume a week is 7 days. So exercise on the weekend as well. Alright, so we start with 3,500, right? We need 3,500 calories to lose 1 pound. So we start with 3,500 calories, right? And 100 calories if we walk a mile. So if we divide that by 100 calories a mile, that gives us 35 miles. So we have to walk 35 miles to lose 1 pound. Now, 35 miles, and we walk in 7 days. 35 miles divided by 7 days. So that gives us 5 miles a day. So that means if we want to lose 1 pound in a week by exercise, we have to walk on average 5 miles a day. Right? Next, there are 4 runners in 1 mile race: Maria, Rita, Thelma, and Debbie. Right? There are 4 people, right? And the point will award to the people that finish in first or second. The first winner get more points than the second. Alright? How many different arrangements of first and second winner are possible? Right, so think about this. If there are 4 of them, right? Any of them can win. I mean, theoretically, we're not talking about ability or whatsoever here. If there are 4 of them, each one of them can win, right? So to choose the first place, we can choose Maria, Rita, Thelma, or Debbie. So that is for the first place finisher. Now, if Maria finishes first, there are 3 people left, and you're going to pick one of those 3 to finish second, right? So we have Maria already. There will be A, T, and D. So that will be MA, MT, MD. 3 scenarios. Now, if Rita finished first, that means Maria, Thelma, or Debbie finished second. And then same thing, we have Maria, Rita, and Debbie. And finally, Maria, Rita, and Thelma. So that in total, we have 12 different scenarios here. And so this problem is not really much. We just list them. The way to list them is a little more systematic. We can pick any one of them to finish first, and then the remaining 3 of them can be second. So we have 4 by 3 here, so that 12 different scenarios. And the question, how many different arrangements are possible? It is not really arrangement. I should say how many possible finish first and second, and then we say there will be 12, right? 12. Right, next. The problem, the grade in marine history class determined by completing 3 tests. So there are 3 tests. Test 1, each test inherent point. So it scored 78 on the first one, 84 on the second, and but still hope to get an A. An A is 94. 92 or above. What is the minimum score she can get on the third test to get an A? Right, so let's make a little table here. Test 1, test 2, and test 3. The average need to be 92 or above. The first test is 78. The second one is 84. What do we need here? Let's just put X. Alright, think about this. If we want an average of 92 and there are 3 tests, so that means if we have 3 tests of 92, 92, 92, that certainly will meet the criteria of getting 92 for an A, right? So 92 is average for 1 test. If we multiply this by 3, that gives us 276 points. So each test, the average is 92, and there are 3 tests, 92 times 3. The total has to be 276. Now if we have 78 plus 84 plus X is 276. Now the rest of solving this problem should not be that difficult. 78 and 84, that's 162. And to solve for X, we subtract 162 on both sides. So X equal to 114. Well, that's not possible because the test is maximum of 100. So even though we find the solution, but the solution is not feasible. So the problem, there's nothing wrong with the problem. It's just this problem has no solution. So meaning that there's no chance to get an A for her. And because we cannot get more than 100. So what is the minimum score she can get on the third test? And we say that it's not possible to get an A. Or in this case we say no solution. So that's why we have to check the solution that we have. Sometimes we have the solution, but that solution doesn't make any sense, or it's not possible to get that number, just in this case. So in that case we just say no solution. There's nothing wrong with the problem, it's just that it has no solution. Right, we just go over a few examples here. The problem solving requires a lot of practice, and depends on the problem. The solution can be different. So we cannot go over all of the different scenarios of the problem that we'll see. I'm just going to do some example here. And with that, we finish section 1.3. Thank you for watching, and see you in another video in Math 1332.